Okay, so we're diving deep today into something I know a lot of you have been asking about. We all know about zero-knowledge proofs, like at least at a high level.
Mm.
That idea that you can prove something is true without revealing any of the secret information.
Right, right.
But the question we're going to tackle today is, how does that actually work in practice when we're talking about verifiable computing?
Yeah. How do you actually apply ZK to make sure that, some computation has been done correctly?
So we're going to assume that you already know a bit about what zero-knowledge proofs are.
Yeah, we're not going to do the basics today.
We're not doing the
It's
basics.
going to be a real deep dive.
This is for people who are already down the rabbit hole with us.
Exactly.
So today's about, verifiable computing, or VC as the cool kids call it.
VC.
And VC is all about this idea that you can have this cryptographic guarantee that a computation was done right. Like you can prove it.
Right. It's not just someone saying, hey, trust me, I did this calculation right. You've got like mathematical proof.
And what's really cool is how zero knowledge can be used to add this extra layer of privacy on top of that verification.
Yeah, like you can prove that you did the calculation correctly without revealing any of the inputs or the intermediate steps.
Exactly. So our mission today is to really unpack how all this works.
Like, how does ZK actually make verifiable computing tick?
And we've got some really great source material to help us with this.
Yeah, we're going to go deep into the weeds today.
So strap yourselves in, folks, because this is going to be a wild ride.
So one of the most important concepts here is this idea of a zero-knowledge virtual machine, or ZKVM,
DJVM.
which sounds super sci-fi.
It does sound like something straight out of like The Matrix or something.
Totally, but it's actually a real thing.
It is, and it's basically a way to prove that any program, any general purpose program has been executed correctly, even if the inputs to that program are private.
Right, so you could have like a program that's operating on sensitive data, like financial transactions or personal information.
Medical records even.
Exactly, and you can use a ZKVM to prove that the program ran correctly on that data without revealing the data itself.
That's incredible. So how does that actually work in practice? Can you walk us through like a typical scenario?
Sure, so imagine you're the one with the program of the private data, right? You're the prover in this case.
Okay, I'm the prover. I've got my secret program, my secret data.
So you run the program on your data, and this produces two things: a public output and a cryptographic proof.
Okay, a result and a proof.
Got it. And then someone else, the verifier, can take your program, the output and the proof, and they can run a verification algorithm.
They basically check your work.
Exactly. And if the verification checks out, they know with very high certainty that you ran the program correctly and that the output is valid, even though they never saw your private data.
So they can trust the result without having to trust you or see your data. That's powerful stuff.
It is.
Now, can we make this a bit more concrete with an example, something that really brings it home for our listeners?
Sure. Let's say you want to prove that, a secret password without actually revealing the password itself.
Okay, that's a classic ZK use case.
Right. So instead of just telling someone your password, you could use a ZK system to prove you know it.
Like, if I knew the password to launch the nukes, I could prove I knew it without actually saying it out loud.
Exactly. And a common way to do this is with something called a hash function.
Okay, I've heard of those. Those are like one-way functions, right? You can't reverse them.
Right. So you take your password and you run it through this public hash function, and it spits out a unique hash value.
Okay, so the password is my secret input. The hash function is the program, and the hash value is the public output.
Exactly. And using a ZK proof, you can convince someone that you know a password that produces that specific hash without revealing the password itself.
So they can be sure I know the right password to launch the nukes without me actually having to tell them the password.
Exactly. They can trust the process without having to trust you or see the actual data.
Yeah, that's wild. Okay, so that's a simple example, but how do we scale this up to proving really complex computations? Like, what kind of real-world applications are we talking about here?
The possibilities are pretty much endless. I mean, think about finance, for instance.
Okay, Wall Street, ZK, what are we doing?
So a bank could use ZK to prove they're complying with regulations like, anti-money laundering checks or capital requirements without revealing all their customer data.
So they could prove they're not doing shady stuff without showing all their transactions.
Exactly. Or you could use ZK to verify the accuracy of like a complex financial model without disclosing the proprietary algorithm behind it.
Right, so you could prove that your model works without giving away the secret sauce.
Exactly. And this is huge because it shifts trust from relying on reputation or audits to relying on cryptographic certainty.
So it's not about trusting the bank, it's about trusting the math.
Precisely.
Okay, so finance makes sense. What are some other areas where this could be a game changer?
Well, think about identity verification, or KYC, know your customer.
Right, where you have to prove who you are to, like, open a bank account or something?
Exactly.
Right.
So instead of having to share all your personal information with every website or service you sign up for,
Which, let's be honest, no one wants to do.
you could use ZK to selectively disclose specific attributes about yourself.
Like proving you're over 18 without revealing your actual birth date.
Exactly, or proving that you're a citizen of a certain country without sharing your passport details.
Okay, so ZK could be a big win for privacy.
Huge. And that's just the tip of the iceberg. I mean, you could use ZK to verify contractual obligations without revealing the full details of the agreement.
Oh, that's interesting.
Or you could use it to ensure ethical sourcing in supply chains.
Right.
Proving that goods were produced under fair labor conditions without disclosing all the sensitive information about suppliers and manufacturers.
So it's not just about verifying computations, it's about verifying properties of data as well.
Exactly, and all this without compromising privacy.
This is really blowing my mind. Okay, so let's get down to brass tacks. How do we actually build these ZK proofs for these complex computations? Like, what's going on under the hood?
Let's take a look at the zk-vm.pdf source here.
Okay, firing up the source code.
And the basic idea is that you take the entire computation you want to prove and you represent it as a sequence of steps, like a detailed record of everything that happens in the program.
Okay, so we're talking about like a step-by-step history of the computation.
Exactly. And this is called the execution trace.
Like a computational audit trail?
Precisely. And the next step is to translate the rules of the computation, the logic of the program, into something called polynomial constraints.
Polynomial constraints, that sounds a bit mathy.
It is a bit, but basically these are mathematical expressions that need to hold true at every step of the execution trace if the computation was performed correctly.
So they're like checks that ensure the program is following the rules.
Yeah.
Okay, I'm following so far, but how do we actually represent the computation and the rules as these polynomial constraints? Like, what does that even look like?
Well, the key is that any piece of data in any state of the computation at any given step can be represented as a sequence of numbers.
Okay, so like the current instruction, the values in memory, any flag, those can all be numbers.
Exactly. And the cool thing about sequences of numbers is that they can be uniquely described by a polynomial of a certain degree.
Okay, I vaguely remember polynomials from high school algebra.
Yeah, don't worry, we're not going to get too deep into the math here.
Please no.
But the point is that we can use polynomials to represent both the data and the rules of the computation, and then we can use those polynomials to construct the ZK proof.
So the program becomes a polynomial and the rules become a polynomial.
In a way, yeah.
Okay, that's pretty wild. But
No.
verifying these polynomial constraints over like millions or billions of steps, that sounds incredibly inefficient. Like, how do we make that practical?
That's where this really clever technique called low-degree testing comes in.
Low-degree testing.
And one of the most popular methods for this is called FRI, which stands for Fast Reed-Solomon Interactive Oracle Proof of Proximity.
FRI, that's a mouthful.
It is, but the basic idea is that it allows a verifier to very efficiently check that a set of values actually corresponds to a low-degree polynomial without having to evaluate the polynomial at every single point.
So it's like a shortcut for checking that the polynomial is the right shape.
Exactly. Think of it like verifying the shape of a curve by just checking a few points along the curve.
Okay, that makes sense. But how does FRI actually work in the context of ZK proofs?
So the prover, who's the one with the computation and the polynomials,
Right, the one with the secret stuff.
they use FRI to convince the verifier that their polynomials are indeed low degree and that they satisfy the required constraints.
And they do this without revealing the actual polynomials themselves, right?
Right. They only have to reveal a small number of evaluations of the polynomials at specific points chosen by the verifier.
So it's kind of like a game of I Spy with polynomials.
Yeah, kind of the prover is saying, I have these polynomials that satisfy all the rules, and the verifier is saying, prove it, show me the value at this point, and this point, and this point.
And if those values check out, the verifier can be pretty confident that the prover is telling the truth.
Exactly. And the beauty of FRI is that it only requires a very small number of these checks to achieve a very high level of confidence.
That's impressive. So FRI helps us verify the polynomials efficiently, but there's still this back and forth between the prover and the verifier, right? Like they have to keep communicating to do these checks.
Right. And that can be a bottleneck, especially if the computation is very complex or if the prover and verifier are far apart.
So how do we get around that?
Well, that's where the Fiat-Shamir heuristic comes in.
Fiat-Shamir sounds familiar.
Yeah, it's a really clever trick. that essentially lets the prover generate their own random challenges without needing to interact with the verifier.
So they can do the verification on their own?
Exactly. They use cryptographic commitments to the polynomials to generate values that look random to the verifier, and then they use those values to perform the checks themselves.
So it's like the prover is playing both sides of the I Spy game.
In a way, yeah, and the result is a non-interactive proof, meaning that the prover can just send the proof to the verifier, and the verifier can check it on their own without any further communication.
That's really elegant. Okay, so we've got FRI for efficient verification and fiat shamir for non-interactivity. What else is there to know about these ZKVM proofs?
Well, the zkvm.pdf source actually provides a really nice example to illustrate these concepts. It's called the Fibonacci virtual machine.
Fibonacci virtual machine, like the Fibonacci sequence.
Exactly. Remember that sequence where each number is the sum of the two preceding ones?
Yeah, 1, 1, 2, 3, 5, 8, 13. I think I still got it.
You got it. So imagine we want to prove that we've correctly calculated a sequence of Fibonacci numbers. Let's say the first 8 ending in 47.
Okay, so I'm the prover. I know the full sequence, but I only want to reveal the final number 47.
Exactly. So the first step is to take that sequence and represent it as a polynomial using a technique called interpolation.
Interpolation. Okay, vaguely rings a bell.
Basically, if you have 8 numbers, you can find a unique polynomial of degree, at most 7, that passes through all those points.
So our Fibonacci sequence becomes a polynomial curve.
That's it. And then we need to express the Fibonacci rule itself as a polynomial constraint.
The rule being that each number is the sum of the two before it.
Exactly. And we design this constraint polynomial so that it evaluates to 0 at all the points in our sequence where the Fibonacci rule should apply.
So if the sequence is correct, the constraint polynomial should be 0 at all the right places.
Precisely. And then we use FRI to verify that the prover's polynomial actually satisfies this constraint without revealing the entire polynomial.
So the prover commits to the polynomial using a Merkle tree and then reveals a few evaluations at points chosen by the verifier.
Exactly. And the verifier checks that the constraint polynomial evaluates to 0 at those points, which gives them confidence that the entire sequence is correct.
And the source also mentioned this technique called mixing. What's that all about?
Mixing is a way to combine multiple constraints into a single check.
So instead of checking each constraint separately, we can check them all at once.
Exactly. And it uses random values provided by the verifier, often using fiat shamir, to combine the constraints into a single mixed polynomial.
And if that mixed polynomial passes the FRI test, we know that all the individual constraints were satisfied.
Right. It's a really efficient way to bundle up multiple checks.
And they also mentioned this deep modification. What was that about?
Deep is a security enhancement. It basically adds an extra layer of robustness to the proof by having the verifier request an evaluation at a point outside the domain of the computation.
So instead of just checking points within the sequence, they check a point beyond the sequence.
Exactly, and this makes the proof more resistant to certain types of attacks.
All right, so the Fibonacci virtual machine gives us a nice concrete example, but how do we go from that to a full-blown ZKVM that can handle any arbitrary program?
Well, the core principles are the same, but the execution trace becomes much richer.
Richer in what way?
Well, instead of just the data values at each step, we now also need to track the program counter.
The program counter? What's that?
Oh, it's basically an index that tells us which instruction is currently being executed.
Okay, so it keeps track of where we are in the program.
Exactly. And we also need to track any status flags that might be set by the program.
Status flags, like what?
Like if an operation results in an overflow, or if a comparison is true or false, things like that.
Okay, so we're tracking the program counter and any flags, anything else?
Well, we might also need to track the contents of any registers that the virtual machine uses.
Registers.
Yeah, think of them like little temporary storage locations within the virtual machine.
Okay, so our execution trace is getting pretty packed now.
It is, but the good news is that we can still use polynomial constraints to verify that all these values are updated correctly at each step.
So we're still enforcing the rules of the program using polynomials.
Exactly. And we even have to account for things like loops and jumps in the program.
Loops and jumps.
Yeah, like when the program doesn't just execute instructions sequentially, but might jump to a different part of the code based on some condition.
Okay, that sounds tricky. How do we handle that with polynomials?
Well, we can use control columns to indicate whether a jump should happen and what the target address is. And then we can use derived columns to update the program counter accordingly.
Derived columns?
Yeah, these are columns whose values are calculated based on other columns.
So like if the control column says jump to this address, then the program counter column jumps to that address.
Exactly. And the source also mentions these external columns.
Yeah.
What are those for? External columns are values that might be computed outside the core constraint system, but are still needed for verification.
Okay, give me an example.
Like, let's say you have an instruction that checks if a number is primality.
Primality testing, that's a pretty complex computation.
It is. And it might be more efficient to compute that outside the main ZKVM and then just provide the result as an external column.
So the ZKVM can trust that external result without having to redo the entire computation.
Exactly.
That's clever.
Huh.
Okay, so we've got all these different types of columns, but how do we actually use them to implement the specific instructions of the virtual machine?
Well, the zkdefvm.pdf source goes into a lot of detail about this. But let's focus on a couple of key concepts.
Sounds good.
First, there's this idea of permutation, which is a way to prove that two sets of values are the same without revealing the values themselves or their order.
Okay, like shuffling a deck of cards, you can prove that the same cards are there just in a different order.
Exactly. And we can use polynomials to do this by checking that a certain product involving the values is the same for both sets.
A product of polynomials.
Right, and we only need to check this product at a single random point, which makes it very efficient.
And this is useful for what exactly?
Well, it can be used for a lot of things, but one example is verifying that memory accesses happen in the correct order.
Like if I read from a memory location and then write to it later, I can prove that the value I wrote is based on the value I read earlier.
Exactly, without revealing the actual values.
That's pretty cool. Okay,
However,
what's the other key concept?
Lookup, which is a way to prove that a set of query values are all present within a larger table of values.
Like checking if a word is in the dictionary.
Exactly, and we can use polynomials and random challenges to do this efficiently without revealing the entire table or the query values.
And this is useful for?
Well, one example is verifying that the instructions being executed are all valid instructions from the program's instruction set.
So we're making sure that the program isn't doing anything illegal.
Exactly. We can check that every instruction is in the allowed dictionary of instructions.
Okay, that makes sense. And there was also this injective lookup thing. What was that about?
Injective lookup is a special case of lookup where you also prove that each value in the table appears at most once in the queries.
So it's like a lookup with uniqueness guarantee.
Exactly. And this is useful for things like memory access, where you want to make sure that you're not writing to the same location multiple times within a single instruction cycle.
Okay, that makes sense. So we've got permutation and lookup. These are like the building blocks for implementing more complex operations.
Exactly. And the zkvm.pdf source actually describes how they use these primitives to implement a whole bunch of instructions for their ZKVM.
Like what kind of instructions?
Like arithmetic operations, logic operations, comparisons, jumps, memory accesses, all the basic stuff that a computer needs to do.
And they do all this using just permutations and lookups?
Well, they also use control columns, derived columns, external columns, and all the other techniques we've talked about.
Right, but permutation and lookup are like the stars of the show.
They're definitely the heavy hitters.
Okay, so let's talk about memory for a second, because the source mentioned that their ZKVM doesn't actually have registers.
Yeah, that's a bit unusual. Most virtual machines have registers, which are like small, fast memory locations.
So how does their ZKVM handle memory without registers?
Well, they use a memory-centric model, where every memory location can essentially act as a register.
So there's no distinction between registers and main memory?
Exactly, which simplifies things in terms of the ZK proofs.
Okay, but how do they handle things like reading and writing to memory if there are no registers?
Well, they use a system of time steps within each instruction cycle.
Time steps.
Yeah, so each instruction is divided into multiple steps, and at each step, the virtual machine might read from memory, write to memory, or perform some other operation.
And they use constraints to ensure that these memory accesses happen in the right order and with the right values.
Exactly. They have a whole set of constraints specifically for memory access, which they label M1 through M6.
M1 through M6, a memory police.
Yeah, something like that. And these constraints ensure things like that memory accesses form cycles of reads and writes, that no memory locations is involved in multiple conflicting cycles, and that load operations retrieve the correct values.
So they've basically created a whole system of checks and balances to make sure that memory is accessed correctly even without registers.
Precisely. And they even have a mechanism called program lookup to ensure that the prover actually executed the intended program.
Program lookup, what's that?
It's a way to compare the execution, trace the record of what the program actually did.
Right, the computational audit trail.
Exactly, to the original program code to make sure they match.
So it's like double checking that the prover didn't cheat and run a different program.
Exactly, it's another layer of security.
Okay, so we've covered a lot of ground here, but can you just walk us through like the big picture steps of how this ZKVM actually works in practice? Like what does the prover do? What does the verifier do?
Sure, so first, the prover takes their program and their private data, and they run it through the ZKVM.
Okay, they execute the computation.
Exactly. And this produces the execution trace, which is a detailed record of everything that happened during the computation.
All right, the program counter the flags, the memory accesses, all that stuff.
Exactly. And then the prover uses all the techniques we've talked about, the polynomial constraints, FRI, Fian-Shamir permutation lookup, to generate an SK proof.
A proof that the computation was done correctly.
Exactly. And this proof is basically a bunch of polynomial evaluations at specific points.
Okay, and then the prover sends this proof to the verifier.
Right, along with the public output of the computation.
And the verifier takes the proof, the output, and the original program code.
Right. And they use all the same techniques to verify the proof.
So they check that the polynomial evaluations are consistent with the program code and the output.
Exactly. And if everything checks out, they can be confident that the computation was done correctly.
Even though they never saw the private inputs.
Right? The ZK proof gives them that guarantee.
It's pretty amazing. Okay, so this approach with the ZKVM, it seems quite different from some of the other verifiable computing methods we've talked about before, like snarks and interactive proofs.
There are definitely some trade-offs to consider.
Like what?
Well, snarks, for example, are known for having very small proof sizes, which is great for efficiency.
Right. Smaller proofs are easier to transmit and verify.
Exactly. But they can sometimes have higher overhead for the prover, meaning it takes more computational power to generate the proof.
And they also rely on these complex cryptographic assumptions that some people find a bit unsettling.
Right. There's this element of trust involved in the setup of the snark system.
Whereas this ZKVM approach using FRI seems a bit more transparent.
It is. FRI relies on simpler cryptographic assumptions, and it doesn't require a trusted setup.
So it's arguably more secure.
But it depends on your definition of security, but it's definitely more transparent.
Okay, and what about interactive proofs? How do those compare?
Interactive proofs can be very efficient for certain types of computations, and they don't necessarily require a trusted setup.
But they can have larger proof sizes than snarks.
Right, and they're not inherently zero knowledge.
Meaning that they might reveal some information about the computation?
Right, but there are ways to make them zero knowledge using additional techniques.
So each approach has its own pros and cons?
Exactly. It depends on the specific application and the desired level of security and efficiency.
Okay, so we've talked a lot about ZKVMs and different proof systems, but can you just step back for a second and tell us why this is all so important? Like, what's the big picture here?
Well, I think the real revolution here is that we're moving from a world where trust is based on reputation or authority to a world where trust is based on cryptography.
So instead of trusting a person or an institution, we can trust the math.
Exactly. And this has huge implications for everything from finance and healthcare to supply chain management and voting.
It could really change how we interact with each other and with organizations.
I think so. I mean, imagine a world where you can prove that you're eligible to vote without revealing your identity.
Or where you can prove that a piece of software is free of bugs without disclosing the source code.
Or where you can prove that a financial transaction is valid without revealing any sensitive financial information.
The possibilities are pretty mind-blowing.
They are. And I think we're just scratching the surface of what's possible with this technology.
I'm excited to see where it all goes. Well, this has been an incredible deep dive into the world of zero-knowledge proofs and verifiable computing.
It has. We've gone from the basics of ZK all the way to the nitty-gritty details of ZKVMs.
And we've seen how this technology has the potential to revolutionize trust and privacy in the digital age.
Exactly. And for those of you who want to learn more, I highly recommend checking out the source material we've been discussing today.
Yes, those are great resources for anyone who wants to go even deeper down the rabbit hole.
And if you're feeling really ambitious, you could even try implementing your own ZKVM.
There are some open source projects out there that can get you started.
It's a challenging but incredibly rewarding field.
So on that note, we'll leave you with this thought. As ZK technology continues to advance, how will it shape the future of trust and privacy in our increasingly digital world?
It's a question we should all be thinking about.
Thanks for joining us on this deep dive.
It's been a pleasure.
Until next time, stay curious.